Okay, good morning or good afternoon, and thank you very much for joining us today. I'm Dan Enthoven, and I'll be introducing John Ju. This webinar is brought to you by Domino Data Lab. For those of you who don't know Domino, we're an enterprise data science platform. We help individual data scientists work and research faster and help teams collaborate more effectively. We also have tools for pushing models into production faster, monitoring performance, etc. John is Domino's data science evangelist. He works with our customers to help them get the most out of their Domino platform and their data science programs in general. Before Domino, John was the program director and director of product at Insight Data Science, where he developed and led sessions of the data science program and was also responsible for growing the Insight Data Science community. John is a PhD in applied physics from Harvard University. Before John gets started, just a few housekeeping notes. You can ask questions on the right-hand sidebar, and John will get to them during or at the end of the presentation. If you want to hide the questions and see the presentation in more of a full screen mode, you can just click the X, and then you'll have a larger view for the presentation. We're going to make these slides and a recording of the webinar available in the next few days, and people that signed up will get an email with links to that. And if you're interested in learning more about Domino, be sure to visit our website, and we'll be happy to set you up with a demo and tell you more about what we're doing as well. Thank you very much, and with that, I'll turn it over to John.
Great, thanks, Dan. Welcome to the webinar, today's webinar. I will be talking about GPU computing for data science, and as Dan said, I am the data science evangelist for Domino Data Lab. My name is John, so let's get started. Today we're going to be talking about why GPUs are useful in the short 30 minutes that we have today. And we're going to go over some examples of using GPUs in data science and what kinds of applications are suited for GPU usage. And then finally, we'll get our feet a little bit wet in figuring out, okay, how from this huge, vast ecosystem, how do we get started in starting to program your GPU? So to get started on why we would ever want to use GPUs in the first place, I want to do a little short case study with Monte Carlo simulations. And so in case you don't know, Monte Carlo simulations are simulations that simulate behavior when randomness is a key component. And so these types of simulations are used in a lot of different fields, from finance to physics to population dynamic studies in social sciences. And so when you have behavior that is random and that part is a key component, you simulate one, but then if you simulate a ton of these, you can average the results, and then at the end of that, make some predictions. You get more information from simulating a lot of things. So just as an example for that, I want to show you what a possible Monte Carlo simulation for finance might look like. Here we have an option price that is simulated. The equation that produces this plot is shown here, where the interest rate and the noise both have random elements in it. And so if you simulate this one time over, you get some information. Because this is inherently a random process, you aren't very confident about what is actually going on here, the results that you're getting. However, if you do these many, many times over, the more simulations you do, the more actionable information that you're getting, the more signal that you're getting. And so here we plotted 50 of these simulations, each simulation having components of randomness in it. And so now we can have information about, okay, maybe at time 20, the probability that the option price would jump to $22 is very low. And then maybe at time 100, the fact that we risk having gains of very small, like 50 cents, that is a very low risk, because you see the price there doesn't really dip down below maybe $22 very much. So this is an example of Monte Carlo. Now, Monte Carlo simulations are often very slow. Lots of simulation data is required to actually validate the models themselves. And so generating all that data, generating all the simulation data takes time. And that's primarily because a CPU, which is normally what we use to do our simulations, works very sequentially. And they're designed to do that. And so as an example, the Mythbusters did a great job in illustrating exactly how a CPU would work. A CPU is designed for sequential, complex tasks. So what they did was they created a robot that was able to aim and translate left and right and aim paintballs at a canvas. And so this machine shot paintballs sequential one at a time at the canvas and eventually created a smiley face on the right. And so this is what a CPU can do. It is a sequential process that happens over time. And they can handle complex tasks such as aiming the paintballs. A GPU, on the other hand, is designed for very parallel but low-level tasks. So as an example, the Mythbusters created this huge machine with lots of parallel paintball nozzles. And so you can see here the paintball nozzles, there are about a few hundred of them on this machine. But each one of those paintball nozzles does one thing. It shoots its paintball straight ahead and does with one color with one paintball. But when this is fired in a parallel type manner, all these paintballs hit the canvas at the same time, and what you're left with is a imitation Mona Lisa painting that is painted in a fraction of a second compared to the previous example. So the applications for GPU computing in data science are numerous. Matrix manipulation and matrix operations, numerical analysis, sorting, fast Fourier transforms, string matching. These are all fundamental operations that a GPU can be very, very good at. Monte Carlo simulations, machine learning algorithms, and search are things that build up on top of these elemental optimized operations that a GPU can be good at. When you wrap up all the things that on the left side and kind of boil it down, the best algorithms for GPU acceleration are as follows. They have to be inherently parallel. It would be great if they use one of these fundamental operations, such as matrix operations, and they take advantage of high floating point operations per second. So flops, if you look in the GPU literature, is something that characterizes how fast a certain algorithm or a certain GPU will operate. So I want to, as an aside, go a little bit deeper into and mention how GPU has changed the landscape in deep learning. So deep learning is basically where you have neural networks that have lots and lots of elements within each hidden layer. And it's not necessarily a deep learning that when you have lots of hidden layers, but it's the fact that each hidden layer has lots and lots of units. And so if you look at the diagram here, you can see that the calculation of, say, an element in the hidden layer 1 is only dependent on the inputs from the input layer. And if you're doing a different type of propagation, maybe the hidden layers in the nodes in hidden layer 2. It is not dependent on any of the other elements within the hidden layer 1. So that makes it great for optimization using a GPU. And so a few years ago, what Google did was create the largest deep learning neural network out there. And so they used 1,000 machines, which used 2,000 CPUs. All that, because they're using 8-core machines, added up to about 16,000 cores. The power they used was about 600 kilowatts. And the cost of creating this vast deep learning neural network was about $5 million. A short time after that, Stanford basically replicated Google's results, but they used GPUs, and they were able to do it using only 3 machines, each of which, and a total of 12 GPUs. And because each GPU has thousands of cores, they were able to get actually more cores involved in the process than Google's data center, having 18,000 cores. And because these machines, there's not a whole lot of wasted energy there. They're specifically designed for this task. They're using 4 kilowatts of power, and the cost is much smaller than the $5 million that Google spent at 33,000. And so what GPUs have done is make machine learning very accessible to the general audience. You no longer need to run a Google type data center in order to do this. And the reason that GPUs can do this is because they're structurally different than a CPU. A CPU has at most 4 to 8 high performance cores, a typical one at least. And each CPU core is designed for very high-level complex things, tasks. A GPU on the right hand, as you can see, has tons of these cores, but each one of these cores is bare bones. And so if you were to actually look at a CPU chip and a GPU chip, a CPU chip would look very complicated because it has to support a lot of the cores there, the complex tasks. The GPU looks actually very, very simple, and that there's lots of cores and a bit of memory, and that's essentially what it does. So that's why GPUs are so different and so good for these highly parallel, low-level calculations. Now, in most computing, in most applications, what you're going to have is a combination of tasks that are suited for GPU and CPU. If you can imagine that your code is a block as shown in the middle there, 90% of your code will be done by the CPU, and it's great at handling that. It is very efficient and works perfectly. But probably there's a compute-intensive function, or several of those functions within your code, and maybe they take up 5% of the code space. But when you profile this, you see that it actually ends up taking 90% of the time to actually execute. And so these tasks are perfect for farming out to the GPU. And so this paradigm of using both the CPU and GPU together is what we call general purpose GPU computing, or GPGPU. Another name that this goes by is heterogeneous computing. And so if you were to look up more information on this, these are great keywords to look at. So now that we know a little bit more about the context of GPU computing, the background, and why we want to accelerate our algorithms using GPU computing, how do we get started? So first thing you need is hardware. You need access to a computer that has a GPU. And the GPU should not be operating your display. So for example, I'm running this webinar on a MacBook Air. That MacBook Air has an Intel GPU built inside of it. But that GPU is powering my display. And so if I were to try to use that GPU for scientific computation, say running a deep learning algorithm, it would be overloaded because it would be trying to power my display and do the algorithm. And so you wouldn't get any kind of speed up there. So where do I get this? Well, you could buy one of NVIDIA's or Intel's, AMD's GPU systems and connect it to your computer. But probably the better way, the easier way, and the more scalable way to do this is to just spin up a GPU, CPU computer. And Domino allows that really easily. So among other things, Domino is great for scalable compute. So here I'm showing you the Domino landing page for your projects. If I were in this project, if I wanted to change my the hardware tier that I wanted to use, I would just go to settings, and available to me are lots of different types of computing instances. And so we can scale from an instance that has a half a core with 0.5 gigabytes of RAM, all the way to something very high performing computer with 32 cores and 240 gigabytes of RAM. Now, most of these, all you really need to know is sort of the number of cores and the amount of RAM that is associated with that computer to get a good idea for the performance that you'll get out of that. A GPU is a totally different animal. Right now, we're displayed here is the fact that this GPU machine contains 8 CPUs, cores, and has 15 gigabytes of RAM associated with that. Now, what it doesn't tell you is the specifications on that GPU. And so what that actually means is that the computer has 8 CPU cores and 15 gigabytes RAM, but the GPU has 1,536 GPU cores and 4 gigabytes RAM. So you can imagine how much acceleration, how much more parallelism you can get with this one, even compared to the most expensive instances which use, say, 32 cores. This is going to be much, much more parallel and give you tons more acceleration. So with one click, you can pretty much check off hardware. Like, so we have settled that we want to use a GPU instance. We clicked on GPU, and so now we have access to that kind of hardware if we're using Domino. Now, how do we get started in the software part? How do we get started programming a GPU? Well, programming a CPU is what we're all used to. It's a very sequential type of programming. So you write code from top to bottom, and the thought process is very sequential too. I mean, you can start linking tasks together, but essentially the fundamental operation is very ordered. And you can do complex tasks while programming CPU, and you never really need to worry about other devices. When you program in a CPU, you can imagine that this CPU is working independently of other cores, of other machines. When you're programming a GPU, it's quite a bit different. Everything is parallel, so you have to think about everything in a parallel manner. Everything is multi-threaded, so you have to start thinking about race conditions when necessary, when you're bringing all that data back together and operating in that way. They're very low-level tasks, so you have to be very specific about what you are asking the GPU to do, and it's also very dependent on the CPU. So communication with the CPU will affect the performance of your code in the end. So how do we talk to your GPU? Well, in the old days, GPU is a graphical processing unit, right? So it's powering the displays, the games that you play, and everything is actually meant to be a graphical primitive. So I'm talking about vertices, I'm talking about texture, and things like that. And so the first people to do scientific computing on GPU had to translate their matrix multiplication code, for example, into graphical primitives like vertices. Now, we don't have to do that anymore, thankfully, because of the advent of CUDA and OpenCL. CUDA and OpenCL are both GPU computing frameworks. CUDA is applied specifically to NVIDIA GPUs. OpenCL is an open source GPU computing framework that is founded from Apple. And these allow us to talk to the GPU without worrying about all of those nasty graphical primitive units. And on top of that, sometimes we can build applications, libraries, and wrappers for CUDA and OpenCL. So thinking about that ecosystem, let's figure out what we would do in choosing how to interface with our GPU. Well, when we do that, it's often a balance, a trade-off between simplicity and flexibility. So there are application-specific libraries out there that are already accelerated, that already have the option for accelerating your code onto GPU. And this is great. You basically don't have to worry that there is actually a GPU out there. You just turn on a flag and do a little bit of configuration, and then you're ready to go. You code exactly the same way that you would have as in a CPU. On the other end, you can write custom CUDA and OpenCL code. This gives you a lot of flexibility in what exactly you want the GPU to do. But the code has to be very specific. It is low-level code, and so the code becomes much more complex, and you have to start thinking about those things like race conditions. Somewhere in between the trade-off between simplicity and flexibility are these general-purpose GPU libraries. And so these are libraries that wrap around some of the fundamental, some great GPU libraries that allow you to do matrix operations, for example, much, much faster. And they're packaged in a way that it seems like you're, say, just operating on normal R or normal Python NumPy. And so that's a trade-off. So when we go into this and think about these our choices, application-specific libraries is definitely one of them. There are a lot of different libraries out there in Python and in R. The Python ecosystem is a little bit more developed than the R ecosystem. Python, you have symbolic math libraries like Theano who can do a lot more generalized computation using a GPU. And then very much more specific things that will accelerate specifically neural networks. That deep learning example, there's really a push to put those on a GPU. And then again, other very specific libraries like ABS, SysBio, which is for systems biology analysis. On the R side, most of these things are very specific algorithms that you want to accelerate. And for example, the first one is a library, a package that allows you to accelerate your fMRI analysis on a GPU. MXNet is neural networks that works for Python and in R. RPUD is a package that accelerates things like distance matrix calculations, SVMs, hierarchical clustering, but very specific algorithms there too. And then finally, RGPU is a package that is great for when you want to accelerate some of your code and analysis in bioinformatics. It's a little bit out of date, but it still works. And of course, we on our blog, on the Domino Data Science or Domino Data Lab blog, we have a tutorial on how to use Theano, Lasagna, and NoLearn to do deep learning. And so I recommend checking that out. It's a very great step-by-step blog entry. So general purpose GPU libraries, that balance between flexibility and simplicity in code. These are great because they allow you to work with fundamental operations. So Python and R both have wrappers for basic matrix and linear algebra operations. Scikit-CUDA and CUDA-MAT are some of those libraries for Python. GPU tools and HyPlarm are great ones for R. And we also have these things called drop-in libraries. So people have created the GPU accelerated equivalent of the common C libraries that we use in our computation now. So BLAST is a common C library that both Python and R and a bunch of other languages use to power a lot of their linear algebra and matrix calculations. What we can tell R to do is say, instead of using the normal BLAST library, we can substitute that in with the GPU accelerated BLAST library called NVBLAST here. And once that occurs, then we can do our normal calculations, our normal matrix calculations in R. And we see a speed up. We see a great speed up because now we're using the GPU instead of the CPU-based BLAST library. And so this also works in Python. If you go to this link, it's a great resource that shows you step-by-step examples, or step-by-step instructions on how to accelerate NumPy using this drop-in library. And the final way to access and program your GPU is using just custom CUDA and OpenCL code. There are 4 steps that usually have to take place when you're doing this. First is to allocate memory on your GPU. These are all very low-level tasks. If you are used to programming in C, these should probably not be so surprising and probably very familiar to you. The second one is to transfer data from the CPU to the GPU. Remember that the GPU cannot operate alone without the CPU, and so there has to be some communication there. The third is to launch the kernel to operate on the CPU cores. And so this kernel is basically instructions that we send to each one of the CPU cores on what to do with the data once it's gotten there. And then finally, it's to transfer those results back to the CPU. So as an example, let's go back to our original example, which is Monte Carlo simulations. And so we're just going to do this using PyCUDA, which interfaces Python and CUDA. And instead of just doing 50, we'll simulate 3 million paths, each with 100 time steps each. So the top top portion is Python code for the CPU. The topmost function there, step, is that equation that I showed before, where the next price is related to the previous price and some noise elements. The Monte Carlo function is what actually drives it. It loops the step function over and over, eventually going out to that 100 time steps. The Python or /PyCUDA code for the GPU is shown below. And as you can see, you do have to edit the code, but it's not a whole lot more code. It's about 8 more lines of code. And so I'm going to show you step by step how we did this. So the first thing we did was to allocate memory to the GPU. And so you can see here that we've initialized empty arrays on the GPU for noise and cur next. We've also, in one step, actually, Python is great for this. In one step, initialized and sent data to the GPU in the middle step there with dcur last. The D stands for device. Oftentimes, the device is the GPU, and the host is what we call the CPU. The next thing we want to do is transfer that data from the CPU to the GPU. I just spoke about how that middle step there does both step 1 and 2 at the same time. And then we want to launch kernels to operate on the CPU cores. Oftentimes, if you don't already have some library that you're leaning on, you're going to have to write some C code here to actually tell each kernel, each core, each GPU core what to do. And so this is a typo here, and in number 3 where it says CPU cores, should be say GPU cores. And so there are two parts where we do this, where we actually operate on the kernel. The first one is the actual time step, or the step that we calculate for the next price, and the bottom one is where we generate our random noise. And so the GPU is great at actually generating random noise because that generation can be threaded out and become very parallel. And finally, we want to transfer those results back to the GPU. And so that path step here, I'm getting all the results from the current step. That .get is what transfers that result back to the CPU, and I'm now storing it in the variable call paths. So when you add it all up, the Python code for the CPU takes about 26 seconds for this to run, and the GPU code actually takes only 1.5 seconds. So this is like a 17x speed up. In general, a good rule of thumb is that the GPU code accelerates much more when you have a lot more data. So if you are operating on a lot more data, if you had Python code that, for example, ran minutes or days, you would expect to see a bigger speed up. So I'll have some sample notebooks at this link where I'll show you exactly the Monte Carlo example that using PyCUDA that I just went over. We'll also have some PyCUDA example compiling CUDA C code for kernel instructions. I'll show you more of a general purpose library in scikit-CUDA where we're doing matrix multiplication. And finally, we'll have an R example where we're calculating a distance matrix using RPUD. So that's sort of what I wanted to talk about today. I hope you got a good idea for how GPU can accelerate your code, an overview of the ways that you can access a GPU through software, through programming languages, through talking to the GPU, as well as a solution for how to access the GPU in hardware and in physical state. And Domino is a great solution for that. I have more resources here, but we'll be sharing the slides, so you can definitely take a look and look at any specific questions or specific walkthroughs that you would like to see. Just to highlight a couple, the NVIDIA how-to sections are great resources. They have great classes there. And the Berkeley GPU workshop, as well as the Duke Stats GPU class is great. So with that, I'll end there. We're a little bit over time, but I'm happy to take any questions.
Great. Thank you very much, John. And as mentioned before, you can ask questions below or type them into the sidebar on the right. And with that, John already has a few to start talking about.
So yeah, Hyun Hwan's asked, I guess, went to the example notebook. Right now, it isn't made public yet, so we have a couple documentation things to add in there so that you can actually access the environments that make GPU processing good. And so we'll be working on that and sending that out in a day or so.
Yeah, and also for those that asked, the links and the slides and all that will be made public as well. Other questions? Okay, cool. Well, we don't have the code on GitHub quite yet, but Domino will be a great place to host this, and we'll be doing that there. Reading the question from Ben.
Right. So Ben says, can a GPU help if I loop through calling many regression algorithms? So yeah, it depends on how you structure the code. So within a GPU computing, as I said, there are lots of different types of ways to access that. So if you're hand coding that using CUDA or matrix multiplication, like that kind of the not application specific type of approach, there's probably going to be some ways that you can structure your data. So sort of like vectorizing this is a great way to go, and that makes looping over things a lot easier. And so this is exactly what we did. We looped over, in the Monte Carlo simulation, looped over through time steps. Yeah, and M. Seligman says that the YDELM package in R can do many small block regressions on the GPU. Great, thanks. Okay. Oh yeah, so what are the volume limits for one GPU? So a GPU, the specific ones that we're using at Domino, they have a 4 GB RAM limit. However, usually GPUs are not known for having like lots of RAM. The way we get around this, a lot of companies actually use GPUs to work with large amounts of data, is to stream data into them. And so that's where that communication between the GPU and CPU is so important, because you're actually holding a lot of that data within the CPU, and you want to just transfer that data. So like the 4 GB of RAM on the GPU is not necessarily a huge limitation. Are there any algorithms that a GPU is not really good for? Well, if your code is not very parallelizable, in that the results depend. It's very iterative, and the results really highly depend on the previous results. And that is probably not a great use for GPU. So really, you want to look for ways that algorithms that are very parallelizable, and that's exactly what the GPU is great at. Yeah, so Tomas asks, does each GPU need to do independent calculations? Are aggregations done by the CPU? The CPU does do a lot of the aggregation, but so when you're actually talking between the CPU and the GPU, there's cost in data transfer in time. So sometimes you can actually do some of those calculations, some of that aggregation on the GPU, but for the most part, since the aggregations are the costliest part of that entire process, and the CPU handles that very well. Hyunhwan asks, are kernels of GPU robust for any looping inside of kernels? I don't quite understand that question. Hyunhwan, if you want to email me at johnju@dominodatalab.com, I'd be happy to follow up with you. All right, so we'll end it there. We're a bit over time. Please feel free to email us, and we'd be happy to share more. Thanks, everyone.